Hello guys, today I will cover center of gravity and centroid and moment of inertia. Again, all of these are very important for strength of material class, so it's better to do review of these topics. So center of gravity and centroid. We know that any object is composed of a near infinite number of smaller particles, each with its own weight and position in space. To make computations easier when performing calculations involving the weight of a structural member, it is possible to replace the weight of the smaller particles with one equivalent resultant weight. So this weight, WR, is given as a sum of the weight of each individual particle. So the resultant weight must act as a specific point in space to be equivalent to the weight of each particle. This point in space is known as the center of gravity. So it is necessary to take the moments of the weights to find the location of the equivalent force. To find the x-coordinate of the center of gravity, you must take the sum of the moments of the smaller particles' weights about the y-axis and set them equal to the moment of WR about the y-axis. So we are starting with the equation WR times x is equal sum of Wn times xn. So using this equation, we can get the x-coordinate of the center of gravity to be x is equal sum of Wn times xn, and we are dividing everything with sum of the weights of all particles. Using the same techniques, we find the y and z coordinates of the center of gravity to be y is equal sum of Wn times yn, and we are dividing everything with the sum of the weights of all particles, the same for coordinate z. Assuming the object is homogeneous, this equation can be reduced to the following set of equations. So if we have volumes, we have integral of x dv and dividing by integral dv. And for areas, we are using integral of x times dA over integral of dA. And for lines, we have x to be integral x times dl over integral of L dl. So we have here some different shapes. For instance, for triangular area, we have that centroid in y direction is equal h third. Area will be bh over 2. If we have a quarter circular area, our centroid in x will be 4 times r, dividing by 3 times pi, and the same for y direction. And we know that the area will be radius on square times pi over 4. Then we have parabolic spandrel, we have general spandrel, etc. Usually, basic shapes are given in FE booklet. For instance, we have example, this is a composite section, and we need to locate the centroid for this area. What we have here, we can divide this section into 3. The first one is triangle, the second one is square, and the third one which we will subtract, will be rectangular area 1 feet times 2. So what we can do, since that we divided this composite section into 3, the area for the triangle will be 3 times 3 divided by 2, which is 4.5 feet square. Then we have for a square 3 times 3, which is 9 feet square. And we are subtracting the rectangle, which is minus 2 times 1. That means minus 2 feet square. So the whole area will be 11.5 feet square. Centroid for the triangle is 1 feet. Then we have centroid for the rectangle to be for the square minus 1.5, and for the rectangle to be minus 2.5, as shown in these two figures. For y, we have for the rectangle 1 feet, then we have for the square 1.5 feet, and we have for the rectangle we have 2 feet. So we are multiplying area times x and area times y, and we will obtain 4.5 for a both for a first section. Then we have for a square minus 13.5 for ax, and for ay 13.5, and for a rectangle we have 5 and minus 4. So using the equation, we can solve for the coordinates, and we will obtain that sum of ax divided by sum of all areas minus 4 dividing by 11.5 will give us minus 0.348 feet. And for y-axis, we have sum of ay dividing by the sum of all areas, which is 14 divided by 11.5, and that will give me the answer of 1.22 feet. The second section is moment of inertia. When finding the centroid of an area, you must find the first moment of the area about a particular axis, that is integral x dA. The second moment of an area about a particular axis is thus given by integral of x squared dA and is known as the moment of inertia of the area. So in some of my previous videos, you saw that moment of inertia is resistance to bending. So the moment of inertia about the x and y axis respectively is given by the following formulas. So we have ix to be integral of I squared dA, and we have iy to be integral of x squared dA. So in many cases, the moment of inertia about axis originating at the centroid of an area are known or given in tables, but to find the moment of inertia about any other set of axes, you must use the parallel axis theorem, because moment of inertia is not constant, it will change. When we are changing the location of the axis, the value of moment of inertia will be different. The parallel axis theorem states that the moment of inertia about an arbitrary axis is found by adding the moment of inertia about a centroidal axis and the product of the area and square of the perpendicular distance between the axes. So I is equal I prime plus AD square, and for Ix we have Ix prime plus area times dy on square, and for Iy we have Iy prime plus area dx on square. So for some basic shapes, usually it is given in FE booklet values for moment of inertia. We have here for rectangle moment of inertia around about centroidal axis, Ix prime is equal bh cube over 12, Iy is equal b cube h over 12. But if we are moving the axes to be x and y, we will have bh cube over 3 and b cube h over 3. So we have here example a moment of inertia for triangle, circle, semicircle. We have quarter circle and ellipse. Here is one example. We need to determine the moment of inertia of the beam in figure about the y-axis. So there are two methods to solve this one. The first method, this problem can be solved two ways, both of which will be demonstrated. In the first method, we will divide the area into three pieces and add their moments of inertia together. So we have the web, which will be 2 inch by 12 inch, and we have two flanges, which are 10 by 2 inches. So for the web, we have moment of inertia, centroidal moment of inertia, bh cube over 12, which means 12 times 2 on cube over 12, which give me the value of 8. And for the flanges, we have bh cube over 12, which means 2 times 10 on cube over 12, and that is 166.67. Since the centroids of all three pieces are on the y-axis, there is no need to use the parallel axis theorem. Therefore, the moment of inertia of the three pieces added together is 8 plus 2 times 166.67, which is 341.33 inch on fourth. Method 2. Another way to look at this beam is a large rectangle with two rectangular holes cut out of the sides. For this method, we will need to find the moment of inertia of the large rectangle about the y-axis, then subtract the moment of inertia of the smaller pieces. So Iy for the first section will be bh cubed over 12, and in our cases it is 16 times 10 on cube over 12, which will give me the value of 1333.33 inch on fourth. And we have Iy to be bh cubed over 12, which is 12 times 4 on cube over 12, that is 64 inch on fourth. Area will be 12 times 4, which is 48 inch on square. Since the centroids of the smaller pieces do not lie on the y-axis, the parallel axis theorem will need to be used. So therefore we get Iy to be 1333.33 minus 2 times 64, which is Iy, plus area, which is 48, times 3 on square, which is a distance from the centroid. And that will give us the value of 341.33 inch on fourth. So the answers are the same for both methods. In this case, adding the moment of inertia was probably the easier method. However, this may not always be the case, so it is upon your judgment how you will determine the moment of inertia. But at the end, you need to get correct answer. So